Well, now I think everyone's been able to join. Hello, everybody, and welcome to our 31st Inspiration Exchange session. For anyone who doesn't know me, my name is Fergus Imrie, and I'm a postdoc in the Schaar Lab, and I'm the host of today's Inspiration Exchange session. And today we're going to be covering synthetic data, but also the topic of simulators. The Lab's very excited to talk to you a lot more about today. Before getting into the session, I want to advertise that our lab is recruiting now for new PhD positions to start next year. So if you have an interest in joining us, please do reach out soon. And in particular, we will have an open day on the 14th of November at 4 p.m. UK time zone, where you'll have the opportunity to meet a lot of members from our group, hear more about us, and ask questions about joining the group in an online session. So please do, if you're interested in this, go to the link shown on the slide there, where you can sign up to make sure you receive information about this session. So now on to today's session. So our session will be consisting of two parts. In the first part, we have several talks from our lab. Professor van der Schaar is going to kick off with an introduction and an overview of synthetic data and simulators. And then we'll have three talks from three fantastic PhD students within our lab, ranging from synthetic data from model testing to a simulator for scarce resources, as well as how synthetic data meets data-centric AI. In the second half, we will have a roundtable with three fantastic guests from industry that I'll introduce more formally later on. And then we'll go into our Q&A session. If you have any questions for any of our speakers today or our panelists at any point during the session, please write your question in the Inspiration Exchange channel on Slack, and we'll put in the chat a link to that if you're not already on our Slack channel. Please do ask your questions as early as possible, and we'll try and take as many as we can later on live during the session. Mihaela, over to you to kick us off with an overview of an introduction to our session.
Thank you very much, Fergus, and thank you so much to our panelists for joining us. I'm so super excited to have us today. So last time we started to discuss about this reality-centric AI agenda, which I have introduced and which our lab is very excited about. And as part of this reality-centric AI agenda, a very important issue is how can we test the wonderful machine learning models that the world is developing in a much more systematic and rigorous way? Because the world is moving to more and more advanced machine learning, but the testing is somewhat still, if I may say, 20th century. So last time, just very briefly, we introduced this new paradigm in AI, which we call the reality-centric AI, which aims to reorient AI towards the complexities of the real world. And if you have not taken a look at it, please take a look at the manifesto that we have written about this agenda. You can find it prominently displayed on our website. And please get in touch and tell us how you think about this agenda. As part of it, one important component is the fact that we need to develop methodologies that are enabling us to much better test machine learning models. Why is that important? Current models are not sufficiently tested. And a good example is the example that I highlight here. This is one of the many examples where a very famous and very prolific in terms of AI company, Google, developed a very accurate model in the lab, but then when they took this model to real application in the real world, the performance was inadequate. And really part of the reason behind that is the current way in which we are testing models using a holdout data set. And what we believe that will be extremely important if it is to make machine learning work in the real world is to build a similar ecosystem for testing that currently other industries have built. And what you see here is the industry of aviation, the aviation industry, which has spent a lot of time thinking about how to test components as well as entire systems such that they work effectively in the real world. Why not do the same thing for the world of machine learning? And Boris is going to be telling you today some of the work that we have been doing to really rethink model testing for predictive models. What about testing of causal models or reinforcement learning models? Well, the challenge here is even bigger because in healthcare, we often need to test not only predictive models, but rather causal effect models or policies that are implementing for decision support. And the trouble with this is that we cannot test these models by trying them on patients. This is medicine where it will be unethical to try new policies on patients. So instead, what we would like to move is from the world of synthetic data to the new world, an exciting world of synthetic simulators. And at this stage, you may say, well, wait a minute, why synthetic data cannot allow for building and estimating policies and causal causality effectively? The reason behind that is because models, for instance, for synthetic data time series generation, such as, for instance, our own method TimeGAN, are not able to disentangle the environment from the policy. So the policy used, for instance, a reinforcement learning policy or a causal effect inference policy is embedded within the data. And hence, we cannot compute counterfactuals by just doing conventional synthetic data generation. So a new paradigm is needed for that. And a few years back, with the development of MedKit, we proposed first solution. However, that first solution had its own limitations. So more recently, Jeroen is going to be telling you about a new way we have been thinking about building such simulators, which allow us to go beyond just testing in an effective way using synthetic data models, but also causal and reinforcement learning models. Finally, we know that synthetic data is important because only when we have high quality data, we can do reality-centric AI. Just having one type of data is not enough. We really need a diversity of data sets. And unlike in ImageNet in healthcare, because the data is about people and their health, we cannot share the data easily. And hence there are a variety of privacy considerations about that. Also, data is not enough, just one data set. We have, for instance, data sets such as Mimic, which is wonderful. But the reality is that if it is to really understand medicines, do discoveries in medicines, and build analytics for medicine that are powerful, we need more than just one data set. So this is also needed because we would like not only one company that may have one data access to build analytics, but rather to allow the entire community of AI to develop the best possible solutions for that. And a potential solution for that we have been pioneering for more than 7 years now. We really were the first academic lab to talk about using synthetic data to allow for development of analytics. And this has been a journey for us. Synthetic data can provide such a solution. And we have a variety of tutorials that we have dedicated to this, and also past sessions of inspiration exchange contain a variety of technologies that we have built on synthetic data. Now, one trouble that has bothered me for some time with our own work and the work of others is that we are creating often not realistic synthetic data, but rather sanitized synthetic data. And this has been an issue that was for the first time very eloquently presented in a workshop at NeoRIS on synthetic data last year, which Sergil, which is one of our panelists, has co-organized together with me and Zhaozhi, who is also of our lab. And as part of that workshop, there was quite a lot of discussion about the fact that the data that we create with synthetic data is sanitized, and is no longer containing the characteristics of the real data, noise, errors, and so on. Hence, we are creating sanitized data that's no longer useful for training reality-centric models. Recently, we have tried to solve this problem, and this is why we combine ideas from synthetic data and data-centric AI. And Nabeel, who is our data-centric specialist, is going to tell you more about that. With this being said, I want to thank you very much for being part of this inspiration exchange, and I look forward to hear your thoughts.
So today I'll be talking about 3S testing, and it's about generating synthetic data for machine learning model testing. And I'll be continuing where Mihaela left off. So we already saw this example where a apparently very good or seemingly very good model in the lab actually doesn't do very well in real life. So this is just one of many examples where a machine learning model is actually not as good as we think. So we need better model testing. Like Mihaela said, we also have this in engineering where actually components are tested very rigorously. But yet we don't really do that. And our objective there is to make that better. Well, so why do we not just use real data in machine learning? One example is that you don't have enough data. So for example, here we have ethnicity and age. We have very few samples for old Black people, but because we have so few samples, this can lead to very high variant estimates of how well a model might do. And as a result, even though we might think that the model does well, actually it does not do well on this population. Of course, this is a problem, and this is a very typical example that we don't have enough real data for smaller subgroups, especially when we see these intersectional subgroups. Another example is that we don't have any data for distributional shifts. So we might have a lot of data from the US, but then using a model trained on US data and we roll it out in the UK, how is it actually going to perform? There will be some distributional shifts, and we might not have enough data to actually measure how well the model will do. So our proposal is to use synthetic data for this. And there's two properties that we're interested in, going back to the two examples that we saw before. For one, we want granular evaluation. So what is the performance on minority groups? And secondly, we want to measure the sensitivity of a model to distributional shifts. So for example, say we train a model on the US and then actually we roll it out in the UK. Can we estimate how well the model will do, or what kind of shifts it might be sensitive to? So what is the actual value of synthetic data? One might ask themselves, if we are using a generative model trained on real data to generate synthetic data, there's no information going into the system. So how can we ever do better than the real data itself? And there's two reasons for that. The first one is that generative models can learn the distributional manifold. So without going into too much detail, here on the right, we see a little figure with very few green dots in the top figure. But there is a clear manifold structure here. Synthetic data, deep generative models might implicitly capture this manifold and model it and actually be able to use that manifold to generate relatively realistic data, and thereby, for example, evaluate a classifier, for example, the dashed line. We also see this in other literature where generative model-based data augmentation has already been shown to help model training. And it makes a lot of sense. We already know that, for example, adding noise to the input of a model can actually help the model be regularized better. But adding noise is in some sense just a very bad approximation of the distribution. So using a deep generative model for that could be much better. So coming to the actual methods that we propose, which is called 3S testing, which stands for synthetic data for subgroup and shift testing, which we are presenting at NeurIPS this year. The method is quite simple. We use conditional deep generative models to create these synthetic data sets. So in that way, we can do both granular evaluation and the subgroup and the shifts. So for example, here we see that we have very few green patients. In the real data, what we do is we train a generative model, we tune it, but then after that, we can actually insert extra subgroup information to generate these subpopulations. And we can just generate the same amount for each, even for the minority group. Subsequently, we use this synthetic data to test a trained model. And in this way, we can, for example, test specific categories, intersections, slices of variables, and points of interest. So, for example, how well would it perform on this one patient? Similarly, we can do this for distributional shifts, where we train, again, a conditional generative model, and then we define a form of shift, and we can actually measure how does the performance of this trained model F depend on this shift. So you might, of course, wonder, okay, but we are not going to be able to model these shifts or these subgroups perfectly. To account for this, we use deep generative ensembles, which is a paper we presented at ICML 2023, where we essentially try to understand the uncertainty in the generative model itself. And this is a little bit inspired by deep ensembles, but here we're using it on a generative model basis. In view of time, I will not go through all the results, but the highlights are that we show that 3S actually enables accurate testing for small subgroups, for shifts, and that we also have good confidence intervals. So I can go into some of these details maybe in the Q&A later. But here we show that we actually do better than the real data in estimating the performance of models. And if we add the real data to the synthetic data, we do even a little bit better. We also show here that we can model the sensitivity to shifts quite well. And again, I can add some details in the Q&A. And we also show that actually, if we have some information of the target domain, so for example, we have a little bit of data from the target domain, we can model these shifts even better. And the more information, of course, we have, the better we can model these shifts. We also show that the model ranking is the same. So if we want to, for example, we have some models and we want to see how well they might do on the UK population, but we only have US data, we can model these shifts, and we show that 3S actually selects the right model better than just using the real data. So, and these are some results on confidence intervals where we are both more accurate, but we also have better coverage. So in summary, synthetic data can enable accurate machine learning model testing, especially for underrepresented groups and for possible future shifts. As such, we see a future where there might be automated model reports using synthetic data. So where we try to probe existing models and try to find failure modes and to anticipate model failures in unseen populations or across domains. The one challenge remains, even though we use the deep generative ensembles, this doesn't give a lot of guarantees. So I think in the future, we will want to go into more understanding what kind of guarantees can we put on the results coming from the synthetic data, or what kind of uncertainty measures can be developed for this.
Okay, so I'm presenting AllSim, which is a new paper that we'll present later this year at NeurIPS. AllSim is a framework which you can use to simulate what the title says, right? So simulate and benchmark resource allocation policies in multi-user systems. So let me explain what we mean by that. Essentially, there are all sorts of problems that would fit into this pretty general category. So I listed a few examples, and let me highlight a few. So in the problem setting of headhunting, we have a bunch of openings that we want to fill with applicants. And to do this, we want to do it optimally using some assignment policy. Or familiar in the lab, in organ transplantation, we have a wait list of patients. We have new donors coming in, such as a liver or a heart, and we want to optimally match the donor given a certain patient. And we measure the success of these policies using either transplant survival rates, ICU discharge in the case of ventilating distribution, etc. So to highlight, we have a few entities in a simulation like this. The first one is obviously a user. And in the case of organ transplantation, that would be a patient. We note it as some X in time, right? So patients come in and go out over time. Same for donors, which we use, we note as an R for resource. and a policy that matches X's to R's or R's to X's. So you denote this as some function pi, right? Very simple stuff. If you observe a system like this long enough, you'll gather a data set. And a data set consists of a bunch of X's, users, some resources, some outcomes like transplant survival, or whether or not someone took a job, and some time indicator T. Now that's pretty awesome. We have a bunch of data sets like this. You have a few open ones even. But there are some problems with these data sets as well. So first of all, there's an in-place policy that completely determines the distribution of this data set. So if we have a policy that assigned resources to X's, so some policy A, let's say, it's pretty difficult to use that data to test how policy B or pi prime would react in the same scenario. The second is users, they arrive in some fashion. Maybe a lot of users arrived yesterday, only one user arrived today, and this obviously also influences how a policy reacts to a certain scenario. So a bunch of the outcome is determined by the arrival rate of users, and similarly for resources. And then finally, a bonus difficulty in this is the outcomes themselves are biased, of course. Like if there is a wait list of patients, we can only assign an incoming organ to one of these patients, not someone who is yet to come or someone who was given an organ yesterday, right? So the outcomes themselves are extremely biased to what we observe at some time t. The way AllSim deals with this, so the general idea of AllSim is we have three components, and these refer to sections in the paper, and the paper will be online in short. Essentially, the first component, so described in section 1, is how do the users arrive? Same, when we have a user arriving, how do we sample? How do we create a new user or resource? And the third is, how do we do outcome inference using these biased data? The answer is, in the first part, arriving users, arriving resource, we model using queuing theory. And you can do it very simply using a Poisson arrival rate, something like that, or you can do it more complicated with Hawk's point processes, etc. Similarly, for distributions in the paper, we use a simple kernel density distribution, but you can do any sort of crazy generative modeling there. And finally, outcome inference, we use counterfactual modeling, which is something that we are quite familiar with in the lab. And you can use very complicated models for this, but also very, very difficult ones as well. Crucially, given this data set, we learn all these components, but we learn them in such a way that a decision maker, such as someone who wants to test a new policy, can influence the distributions themselves through these interfaces. So with a new queuing arrival rate, you could essentially tweak this arrival rate in such a way to model the situation that you're interested in, and then you can run your new policy and see how that reacts. So with this, we can build some scenarios, right? So we expose a very simple API, which is why it's a benchmark track paper. You can use this as well, where you build a simulation using some keywords, some keyword arguments. You add in a data set, such as the open source UNOS data set for organ transplantation, and you build a policy which you can evaluate in the simulation. And the result is a new data frame. So this is a pandas data frame that models exactly the type of data set that we introduced earlier, but then given your new setting and your new policy. So as an example, what we did is, to see how accurate this thing really is we learned some arrival rates from a real data set. We learned 4 different arrival rates, one for each age bracket. So this is an age bracket for a donor. So a donor that's less than 30, donor between 30 and 45. And what we see is, for example, the donors between 30 and 45, they drop over time slightly. And given this very simple setup, so this is the only thing that we learned from the way in which donors arrived, we can model a pretty accurate simulation already. So this is very rudimentary, but it results in quite a good approximation of what actually happened in the data. Of course, the more refined you get here, the better this thing will become, right? So what you see is donor age is obviously increasing. That's nice, and it's makes sense because this low bracket is actually decreasing. And then correlated with this is BMI is also increasing slightly in humps, which makes sense. Older people apparently have a higher BMI. So, okay, that's great. It seems to be realistic. What can we actually do with this? Well, as an example experiment, what we did is we took some liver data, some liver transplantation data, and we observed, or we created a new setting where the amount of livers were declining in such a way that they did during COVID-19. And what we see is on the solid line, we see what would happen if there was no COVID, so no decline in livers, versus what would happen if COVID actually did happen in this time frame. And steadily, we see, given the same policy, exactly the same settings, but for the arrival rates of livers, we see that the amount of additional life years gained after transplantation steadily dropped in COVID times, which is also what we observed in reality. As another, we could also test different assignment policies. So MELD and MELD-NA are very well-known liver assignment policies, and we wanted to see how good is it compared to like this really dumb first in, first out assignment policy. And very happily, we conclude that FIFO is actually doing a lot worse than purpose-built assignment policies. But crucially, for the first time, you could actually test this in a way that is exactly the same. So all settings are exactly the same, but for the policy that we want to test. AllSim is a pretty general framework, so I gave some examples in org transportation, but you can use any type of assignment allocation problem that I mentioned earlier in my talk for this, and AllSim will be provided as a free-to-use open source framework. Furthermore, we also use it ourselves, so we are currently working in the org transportation setting with some clinicians, where we use AllSim to actually do some testing for new policies. Some of them were already published in NERPS and ICML. Finally, we believe AllSim will really aid a variety of fields beyond organ transplantation and encourage researchers to actually build more policies, because the most annoying part of building policies is trying to get a good convincible simulation up and running before you can actually see if your idea works in practice. So that's it. Thank you.
So hi, good afternoon, everyone. My name is Nabeel. I'll be presenting our paper, Reimagining Synthetic Tabular Data Generation through Data-Centric AI, a comprehensive benchmark. And this was joint work with my fantastic co-author, Lasse Hansen, who joined us in the group from Aarhus University, along with Mihaela and Andrea Petrovic from the University of Belgrade. And this paper will be at NERPS 2023 Datasets and Benchmarks track. So I think we all know that synthetic data proposes to really fuel machine learning, particularly in many cases when data sharing becomes some sort of an issue, when we have access limitations, issues around fairness, or when we want to maybe run competitions. And the thing is, when we have synthetic data, what we really want is high quality synthetic data, which really mirrors real data. And when we think of synthetic data mirroring real data, we want this to include all of the nuances of real data. And this can include things such as noise, mislabeling, and measurement artifacts that we find actually in real data. And if we really don't account for this, we show in this paper that synthetic data has the potential to actually sanitize data sets. And then when you actually take such models trained on this data to real data sets at testing time, we actually have many failures which can harm things such as from the aspects of model selection, feature importance, and actually downstream performance as well. And you might say, can't we just assess statistical fidelity? And we show that statistical fidelity simply is not enough. For example, you have a variety of generative models on the x-axis, and we see there that they actually have different performance from the actual real data. And we see that if we assess statistical fidelity, for example, inverse KL divergence, we see all of these models are actually pretty good, and hence we might not notice this discrepancy. And the key idea of this work is, can data-centric AI help? And particularly ideas of data characterization and data profiling to shed better light to guide the synthetic data process. And the answer to this is yes. And we see that by using these ideas from data-centric AI in terms of getting different profiles of the data, easy samples, ambiguous samples, hard samples, we can actually more nuancedly capture when synthetic data or generative models themselves are actually going to reflect our real data sets. And for this here, we build a benchmarking framework where showing how can data-centric AI actually guide synthetic data. So imagine we have a data set that we're going to partition into some train and test set. We actually can start with a data profiling pipeline, which effectively wraps your conventional generative model. We can either start with doing these profiling as a pre-processing step before fitting a generative model, actually getting these profiles and then fitting generative models on the different profiles themselves, thereafter fitting the generative model, or we could do it as a post-processing on our actual data sets that come out of our generative model, so the synthetic data set, and get these profiles and assess how well do they match real data. So once we have these three in this pipeline, which we'll be using as our benchmarking framework, we can then actually perform model training, both on our synthetic data and real data. And then we can do evaluation, not only on statistical fidelity, but also in terms of classification performance, model selection, and feature selection, and really understand what do different generative models do for these different important tasks that we actually want. And for this year, we conduct, using this benchmarking framework, a broad study across 5 different generative models, from GANs to VAEs, Bayesian nets, normalizing flows, and diffusion models. We look at 3 different data-centric methods for profiling across multiple data sets and across a variety of tasks. So I encourage you to take a look at the paper for many more details, because we have many experiments. But what I really want to distill today is some takeaways and practical guidance that came through this broad-scale benchmarking exercise. So the first is, we show that statistical fidelity simply is just not enough. We show that while statistical fidelity might appear very similar across generative models, we see quite significant performance differences when you think of different tasks you might use the synthetic data for, whether it's actually reflecting real model performance, or it's selecting between different downstream models trained on a data set, or actually just from a feature selection perspective. And the tip that we come from this year is that one, when using synthetic data, really needs to keep these 3 tasks in mind when assessing generative models. The second is that different generative models are actually just really good for different purposes. If you want to retain characteristics of your actual real data, we show that methods such as TabDDPM, CTGAN, and TVAE are pretty good at this task. If you want specifically to think about matching classification performance of real data, we show that TabDDPM stands out there. From a model selection perspective, CTGAN, and from a feature selection perspective, TVAE. And what we find quite interesting is that actually no model or generative model reigns supreme across all of these tasks. But if you were to pick one, CTGAN and TVAE do offer quite a good trade-off of both statistical fidelity and these 3 downstream tasks that we look at. And finally, bringing these 2 areas of data-centric AI and synthetic data together, we show that data-centric methods themselves can improve statistical data, synthetic data utility. We show in the paper that both pre-processing and post-processing via data-centric methods can actually help generative models when we think of all these different tasks, and really bring synthetic data closer to real data, not just on fidelity, but on performance, model selection, and feature selection. And we see this effect is especially pronounced on data that has noise, showing the real potential for data-centric AI is really a plugin to help synthetic data methods. And the tip here is that one should think about applying data-centric methods simply as an add-on to your current generative process, for example, as a pre-processing to your data to get these data profiles before fitting a generative model. So ultimately, to conclude, we've shown that there is a potential for data-centric AI to really guide the generation of synthetic data to be more representative of the real world, and this potential for this interaction of work at the interaction of data-centric AI and synthetic data, and more can definitely be done here. Thank you.
Okay, here's a quick update about the Synthcity package, which is a library that our lab has developed as it's maintaining, that offers an array of synthetic data generation and evaluation methodologies. So this is a big update after the summer months. We have implemented a variety of new models, including an adversarial random forest, which is actually the first forest-based generator inside Synthcity. You may have explored random forest for classification, but you should try how this type of forest or tree-based models work for data generation as well. We have also included generation of realistic tabular data or grades, and this is our first LLM-based generator in the Synthcity. And we've also added AIN, adaptive and iterative mechanism for differential private synthetic data, which is one of the state-of-the-art method for generating differential privacy synthetic data. On the metric side, we have added a new metric called DOMIAS, which is aimed to evaluate the risk of membership inference attack using density estimation. And beyond that, we have made all sorts of improvements about tutorials, adding a plugin registry for easy benchmark and various bug fixes. So what's coming next? We have planned a lot of new plugins and metrics, including Stacy, which is a score-based tabular data generative model. So if you want to play with score-based models or you're interested in things like diffusion model, be sure to stay tuned and check that out. We also have 2 new methods for for private synthetic data lined up, adversarial instantiation and private synthetic data for multitask learning and marginal queries. And of course, we're going to implement more methods that has been recently accepted in NeurIPS. And we welcome the community to contribute any new issue and new pull requests and join our developer program. So in the upcoming NeurIPS conference, that is around 1 month from now, Synthcity will be presented as a poster in the dataset and benchmark track, and it will also give an opportunity to really illustrate how Synthcity can help you. At the same time, we are hosting the synthetic data workshop for a 2nd time in a row at NeurIPS this time, and it will be co-organized by Sergey, who is a panelist here, me and Mihaela. And be sure to attend this workshop if you are around and join the community of researchers and practitioners to discuss recent topics about synthetic data and simulators. Thank you.
So I'm excited now to move into the second half of today's session and to move to our panelists and introduce our 3 guests today from industry. Our first guest is Dr. Rianne van den Berg, who's a principal researcher at Microsoft Research in Amsterdam. Also joined, as Zhaozhi mentioned, by Dr. Sergey Aidor, who is a senior applied scientist at AWS. And finally, but by no means least, we're joined by Dr. Maya Rudolph, who is a senior research scientist at the Bosch Center for Artificial Intelligence. So I wanted to kick off the panel discussion today by asking each of our 3 panelists just to touch on how synthetic data and simulators are used at their companies, and maybe some real where they see the main opportunities for these technologies. So I don't know, maybe Rianne, if you could kick us off.
Yeah, first of all, thank you for inviting me. It's a super interesting seminar so far. So I work at Microsoft at AI for Science, and so in our case, the most synthetic data that we're using is actually the data that's coming from like computational simulators for the natural sciences. So for instance, simulating how molecules wheel around in space. That is a very classic, I would say, example of synthetic data. And then the real data typically is a bit more sparse. So if you would want to compare against real data, you would look at, for instance, experimental measurements, which in the case of, for instance, molecules wiggling around would correspond to saying an average of some statistics that you calculate over trajectories of molecules wiggling around. So that's how I'd say a typical example in our case.
Awesome, thank you. So
hi, everybody. Thank you so much for having me in this amazing event. Actually, all the talks have been really interesting. So yeah, I'm a senior applied scientist at AWS AI, and I've been leading efforts mostly about privacy. And so because of this, we were also interested in synthetic data generation. Actually, one of the items that Zhaozhi mentioned as like future task was our paper. So for us, I think I can mostly talk about the data exchange component for synthetic data. But before that, we were interested in 3 different directions. So one was data augmentation. Can you use synthetic data for data augmentation? And another one was model testing. I think the first talk was about that. And then the latest one was data exchange. And based on our experimentation and research, we realized actually synthetic data was most useful for data exchange, at least for in our cases. So if you want to collaborate with different parties, for example, instead of handing them over the exact data set, you can generate a data set that mimics it, but using some differential privacy guarantees, you can make sure that they cannot infer any sensitive information from that synthetic data, and that data could still be used for machine learning training. So that has been our main focus, and we saw that it could be used for data exchange if you want privacy guarantees.
Thank you for sharing, Nabeel. Maya, do you want to talk about this from your perspective at Bosch?
Sure, I'd be happy to. So hi, everyone, and thank you also from my side. So in the past years, I've been working a lot on self-supervised anomaly detection. And there, synthetic data is relevant from a few perspectives. So first of all, when we do self-supervised learning, we need to have good data augmentation techniques. And there, since a lot of the data we deal with is beyond images, so we've been spending time thinking of how to learn, how to best augment time series data, tabular data, graph data. So this is one aspect of it. And then even more intriguing aspect, because it's so much more difficult, is this direction of model validation that has already been mentioned. So especially, let's say you train an anomaly detector, it already works really well in like certain settings, but then you open a new factory or you want to deploy it in a new, like with anomaly detection in particular, anomalies are so rare that you can't validate it in a new setting. And so we've been spending a lot of time thinking of how to use synthetic data to at least convince yourself that maybe your algorithm will work well. And so it's really exciting that in the last few years with diffusion models, we really see such a boost in the quality of generated data. And yeah, looking forward to discuss more about, how can we, so already, I think Boris mentioned that statistical guarantees is something that would be really nice to get. And that's already something that's hard to get when you work with real data. And so I think there's a lot of very interesting research questions there.
Oh, thank you so much. And I think what was really cool for me there was that's three very different kind of sets of use cases and applications of some of the same technologies. So I think there's definitely great opportunities in many areas. Boris, I think you had a question you wanted to ask, you wanted to pose to Rian.
Yeah, so it touches, I think it's actually quite relevant for all the panelists, but I'll ask it to Rian. So I think we've mentioned it before. So to what extent can we quantify the quality of synthetic data or generative models for that matter? So for example, the ability to model out of distribution is inherently limited and quite uncertain because it is out of distribution. And I guess in the context of your work, Rian, of modeling, say, molecular dynamics using diffusion models, how do we ensure that the model actually works for larger molecules for which, for example, a physics-based simulation may not be possible?
Yeah, so I think if we manage to answer that, we're getting ourselves a really good next research grant, I think. I think that's one of the big questions that currently resides in most of the, say, AI for science, natural science field. So imagine that you're, for instance, trying to learn with like a machine learned force field that tells you if your molecules are wiggling around in this space, how to move around, right? you can train it on the data on the synthetic data that you've generated for one size of molecules, but you want it to work for the larger sizes because that's what you started. That's the whole point, right? Because the actual physical simulators can't deal with that. I guess I don't know how to quantify it. I guess there's a lot of approaches on that essentially try to, see if you can get some trends in terms of scaling correctly for the data that you already have. But how to quantify that, I don't know. That's really difficult, right? So out of distribution detection is super difficult. And I think it's again, a little bit the same here, right? You will necessarily go out of distribution, but how to do that is, I don't know, that's incredibly difficult. And how do you know that a single sample, for instance, is out of a distribution? That's already an ill-posed question by itself, right? You can, unless your distribution has a finite support and you're going out of that support, that whole question is ill-posed. So, yeah, I don't think I have a much more satisfactory answer than that.
Let me throw a ball, Fergus, to Nabeel. Nabeel, would you like to say something about hardness and hardness of examples and how it relates to this?
I think it's probably, when you think of at least example hardness in a lot of this data-centric literature, it links to a lot of atypicality of samples. So even if it might lie within the distribution, the sample is just inherently very atypical. But I think the biggest challenge there when you think of generating synthetic data for even these atypical samples is once again quantifying the degree of uncertainty there. And I think that's a non-trivial challenge at least.
Can I ask a question then to that, if that's okay? So typicality,
yeah, please
right?
do.
Typicality you can only do, I mean, how do you define typicality, right? Typical sets on any non-trivial distribution is super difficult to quantify, right?
Yeah, I guess at least what people have started looking at, it's either atypicality, if it's in the more trivial sense, would be with respect to like some neighborhood of your distribution. But then additionally, if it's really hard when you think about a downstream task and say with respect to the model's ability to learn certain samples, some samples that are atypical are going to exhibit certain properties when the model starts learning them as a proxy to quantifying this when the distribution itself is really hard to say that a model has an inability to learn it. So this might provide signal towards its atypicality. So I guess maybe there's two, but I think there's probably a lot more that should be done to make it a bit more rigorous, especially on the second scenario I described.
Awesome, thank you, Nabeel. I think you had a question for our panelists as well that you wanted to ask. Yes, that might touch on some of these points as well, but might be a bit different as well.
Yeah, so I think it's probably anybody on the panel could probably take this question, but I guess in all of your different companies or fields, what would you say is the biggest barrier to adoption of synthetic data? And not so much from like the technical audience who knows how synthetic data is used, but from maybe a more business side who might consume the synthetic data, and what would be barriers to limitations there that needs to be addressed from like a research perspective to make people more confident of using synthetic data?
So, Laura, Maya, perhaps one of you want to kick us off on this question.
I will reframe the question a little bit. So I think already it's interesting to ask what are the biggest barriers for adopting machine learning models themselves. And so I guess there at Bosch, we care very deeply about quality and knowing, there's this long tradition of engineering practices, and there's very fine protocols on how to validate engine components before we let it on the street. And so we try to bring the same standards to machine learning models, which is very hard. And I feel like now if we even go, already there's always the question, if we have this black box model, what kind of data was it trained on? And now, on the one hand, we are hoping that with synthetic data, we can help model validation, right? We can, let's say we care that driving assistance model that we trained on Autobahn driving data in Germany, that it also works well in the UK. I guess hopefully now we will be able to generate this kind of data. But from a statistical learning perspective, I feel like we are only compounding the problems, right? Because now there's additionally the moving target of the training data that was used to train the simulator for generating the synthetic data and so forth. So kind of, I actually want to throw this question back, maybe at Boris, because it relates to his talk, but also to the results that Nabeel showed us, where you kind of use, say, synthetic data for model selection. So how sensitive are those results to the training data that you use to train your simulator? And how do you think about this at all?
Yeah, I mean, for us, it's entirely dependent on the data, of course, that we feed into the generator. So, and I think that's a big question a little bit also for the field. Like, how do we expect to do better than the real data? I think what we've tried to do is at least try to understand how much does it depend on, for example, the specific draw of the training data of the generative model, and also the training dynamics of the generative model itself. So I was already referring to this work that we also presented, ICML, Deep Generative Ensemble, where we try to at least try to capture the uncertainty in the generative model. But yeah, no, I think it all depends on the training data in the end. I don't know whether you want to add something to Nabeel. Nabeel was of course also a co-author on this paper.
Boris, maybe you can say something about a little bit more, because I think you just allude to the ICML paper, but you may want to say what is happening in that paper and why you think would be a solution for uncertainty, because I think that will be useful to hear the panelists' opinion on that.
Yeah, I guess what we were inspired by is deep ensembles and supervised learning, where you actually see that if you just train a supervised deep model multiple times, you kind of capture the uncertainty of the model. So you, in some sense, try to model the distribution over the model parameters. And here we're trying to do it on the generative model side. So we take multiple generative models, we generate different synthetic data sets, and the differences between the synthetic data sets is a implicit measure of the uncertainty in your synthetic data and in the distribution you've learned. And in the paper that we've written, it's only a start, I think. It doesn't come with a lot of guarantees, but it does have big implications also on how you should publish synthetic data, because we kind of show, well, if you just publish one synthetic data set, for example, with privacy concerns, and actually that's one synthetic data set doesn't actually capture your uncertainty or the errors in the synthetic data itself. So either you have some other method of actually explaining how uncertain it is, but just publishing different synthetic data sets with these differences kind of capturing the uncertainty is already a way of doing that, and that's what we go into in the paper.
Maybe I can add a few comments here. So we actually found it really hard getting better results than just the real data, at least for the tabular data sets. I'm not saying we did the best kind of research, but we tried so hard, and yes, still the results were not much better than just using the real data set for different use cases. And then our hypothesis was that you need some additional data or additional information to make them work. So it could be through LLMs, for example, this approach that Zhaozhi mentioned, the approach called GRADE, that they are planning to integrate into Synthcity. It is kind of using that external information. It is using large language models to bring new information to generate better data sets. So that would be one thing. And I also want to mention one more challenge we have, which is a little bit a trade-off to the data quality. So if you are interested in preserving privacy, so there is, when you want so much privacy, then you lose utility, or vice versa. So the right balance between these two has been the biggest challenge for us, actually, for generating synthetic data with privacy.
Thanks for sharing that. So that's really, really, really interesting perspective. And thanks, Maya, as well, for some of your comments on that topic. Mihaela, I think, did you have a question about simulators that you wanted to pose to our panelists?
Yeah, so I like there is already in the chat a question from somebody in the audience asking, I think May is asking a related question. So I'm very, as somebody that has worked on synthetic data now for quite many years, even with previous generation of students, I'm excited about this new angle, looking at data and synthetic data for simulators, and especially for a topic not only like in AI for science, like Rian said, but also for simulators in medicine, simulation in other areas that we cannot experiment really on people. So trying causal effect inference, treatment effects, policies is difficult. This is what we've been struggling for quite some time. You have seen what we have done with Jeroen. We have a prior work that tried to go in this direction, but we find this hard. So I was curious, what do you three think about this area, and how do you take this world further? Maya, it seems you have some thoughts. I guess this is very related to Bosch's work, I guess.
Yeah, for sure, very related to Bosch. I really was impressed with Jeroen's talk. I guess that's why I was nodding, that I think it's really cool. I personally don't work in RL so much, but it did trigger some thoughts that would be really fun to use it to, yeah. So on the bigger picture, I guess at Bosch, there's like a very long tradition of building simulators, of having like physical models. But those we understand quite well, and they're not usually derived from data. They're, derived from first principles. And one topic that we've been thinking about a lot about is how to bring that together with the world of machine learning. But so far, to be honest, we've been thinking about that more from a model building perspective. So, and not, we haven't thought about using synthetic data in that context yet, not that I'm aware of.
Very interesting, Maya, because that's to some extent what we try to do here. We try to bring the world of queuing and queuing theory, which is part of my past life. So I used to be a communication engineer at some moment in time in my life. And there we were building a lot of mechanistic models using queuing and queuing theory to build the internet and to build wireless networks. But there was no real data involved. Like you said, we were doing more minimal measurements to kind of ingest parameters for these queuing models. But in medicine, unfortunately, we do not know the laws. So kind of the trouble there is, if we do not know the laws, how to go think about that. So I'm really hoping that we kind of make the community more enthusiastic to think about this challenge, because we find it interesting.
I think it's something I've also seen in more of the kind of computational chemistry space as well, where molecular dynamics were typically purely physics-based, almost from this first principle, as you mentioned, Maya, and now people are trying to use kind of machine learning there more to speed up is where I've seen it, because they require you to take lots and lots of these small physics steps, whereas maybe you can kind of coarse grain some of these things. So I agree with you. I think this is a super exciting area, maybe we look to combine some of these learned simulators with kind of simulators from kind of first principles. I want to, in the interest of time, try and take a couple of questions from the audience. So I think there was a question in the chat from Yashi Zhang. Are you here, and do you want to unmute yourself and briefly ask your question? If not, I can read it out for you. Okay, so I will briefly read out the question, which is, I think it's for Boris, and this is about what are the benefits and drawbacks of using synthetic data compared to, say, upweighting minority points, and with a little bit about how maybe this can accurately capture correct representations in the data.
Yeah. So I think two questions. The first one is about how does it compare to real data evaluation on these small subgroups? So what we show in the paper is that we do better on evaluating, especially the small minority subgroups. So as a result, if you would be interested in overall performance, but you would just upweigh the small minority groups, then our model will be better because we do better on the upweighted samples. So yeah, we do better than real test data. Then the second question is very interesting. Like, how do you guarantee that you capture the right, say, correlation, but in general the right distribution? And this goes back a little bit to what we've been discussing in the panel discussions, that we cannot actually guarantee this. But the fact that we do so much better on our metrics, especially for these small subgroups, should be quite reassuring. We also use this deep generative ensemble that I've mentioned to actually understand how uncertain we are. This includes, for example, correlations. But in the end, yeah, you are right. It's super interesting whether it would be possible in the future to give guarantees on the quality.
Thanks, Boris. If I may elaborate on almost the first point very briefly, I think one of the differences with kind of upweighting points is more in the diversity. If you upweight, you still have the same number of potentially very few samples. So you're more exposed to that kind of random chance for, oh, for these two samples, the model was either very good or very bad, and upweighting those just almost amplifies that. Whereas I think one of the key ideas of using synthetic data here is we can get a more diverse representation of that class of interest, and hopefully that kind of stochasticity or randomness evens out a little bit, which is one of the reasons, at least intuitively, of why this should work a little better. I think we've got time for one more question, and I think we're going to I'll ask Friso for their question. I think it's for one of our panelists, Rianne. Friso, I don't know if you want to unmute yourself and ask your question.
Yes. So very interesting, all the talks, and thank you very much, everybody. I had a question about synthetic data. When your experimental data is like an aggregate of the physical process. So for example, in the molecular case, typically you have only this limited perspective, which is the product or the sum of the physical processes. How do you create useful, accurate, and robust synthetic data when you only have this aggregate view of your data?
Yeah, that's a great question. I think if you want to think about synthetic data in the area for molecular simulation, I guess the question is, what do you want to use the synthetic data for? Right? Is the simulator itself, like the physical simulator from first principles, already the synthetic data, or is it, for instance, supposed to mimic the data that you refer to, right? The aggregate data. And your question is how to get reliable data for the second case. Is that the question?
Yeah, in this case, I'm specifically interested in not the aggregate view itself, but the actual reality, the underlying reality. One way of thinking it is cryo-EM. You have all these limited pictures, but you try to create a uniform model of what's actually happening. Yeah. And using synthetic data to help you, for example, inform your prior distribution to get a more accurate prediction of what's actually happening. How do you make sure that you create accurate synthetic data when you don't know exactly what's happening and you have only a limited perspective?
Yeah, that's a good question. I think I like the cryo-EM example. Okay, yeah. So for cryo-EM, imagine indeed that you have some weird, like some generative model that creates this 3D volumetric, a model that creates a like a 3D view of the proteins you're supposed to. How do you make sure that gives you valid, projections, so to speak? I guess is your question, right?
Yes, you want your molecular model. You don't want only the 3D view, but you want the molecular model of what's actually happening inside. How do you make sure you can synthetically generate useful data?
Okay, so you're asking, if I imagine that I have a model that gives you like a voxel. I'm trying to dig into this because otherwise it's hard to understand. You're saying, imagine that I have a generative model that creates like a 3D voxel representation of my protein or whatever, right? Is your question, how do I make sure that if I would map that to an actual molecule, that actually makes sense? Is that the question?
Because you have the wiggling, for example, and if you see the wiggling in the cryo-EM, you only get this statistical view. You get like the average of all the wiggles. So how do you make sure you get the molecular model and create synthetic data that's useful in this kind of situation?
I guess one way to maybe try to do that is to make sure that your, say, voxel-based representation has some inductive bias in it, that it must come from some physics-inspired, graph generation that you then voxelize. I guess that's one way to do it. I guess ideally you would like to actually validate it on some real cryo-EM data, right? Validation, you can't only do it by putting in physical priors into it. I guess you also want to make sure you're looking for, how can I validate it based on some actual real data? That's the question.
Yeah, in this case, it's hard to validate because you only have the limited view. You only have the limited perspective. Yeah. You don't have the actual physical model. So validation is limited in that case.
You could validate on a held out set of type of proteins, right?
Yeah.
For which you have already done it. You could try to do something like that. I guess that's the simplest thing, in which I'm sure many people have thought about already. Yeah.
Thank you.
Thanks, Rhiannon. Thanks for that super tough question to end us on. I think with that, especially given time, we're going to start now wrapping up. Obviously, I want to say a massive thank you to our three panelists, Rhiannon, Sergel, and Maya. And I want to briefly just say a few more words to close up. So our next session on personalized monitoring will be next month on the 4th of December at the same time. As I mentioned at the start of the session, we are advertising for PhD positions within the Schaar Lab. And so if you have interest or know anyone with interest, please do attend or point them towards our virtual open house on the 14th of November for that. With that, I'd like to just say once more a huge thank you to our speakers and our three guests, Maya, Sergel, and Rhiannon, and look forward to seeing you all next time. Thank you very much, everyone.